Picture this, a colossal concrete arch, reaching hundreds of meters into the sky, designed to tame a mountain river. This was the Vajont Dam, a monument to human ingenuity in Italy's spectacular Dolomite Alps. But on October 9, 1963, this engineering marvel became ground zero for an unimaginable catastrophe. A massive landslide plunged into its reservoir, unleashing a tsunami that obliterated entire villages and claimed thousands of lives. This wasn't just an accident, it was a complex dance of geology, hydrology, and human decisions. We're going to perform a forensic engineering analysis, counting down the critical factors that turned a dream project into a nightmare, revealing how geological warnings were tragically ignored. Coming in at number 19, we have the sheer, majestic geography of the Vajont Valley itself. Nestled deep within the Dolomite Alps, this narrow, steep-sided gorge was, on the surface, an ideal location for a hydroelectric dam. The topography promised a large reservoir with minimal surface area, reducing evaporation. However, what appeared as a blessing was a profound curse. The valley's extreme slopes, formed by ancient glacial activity and tectonic uplift, hinted at a deep-seated instability. This dramatic landscape, while beautiful, was a geological time bomb waiting for the right trigger, a reality that was gravely underestimated. At number 18, we delve into the very heart of the problem, Mount Toc, the mountain towering above the dam. Geologists knew there was an ancient landslide on its northern flank, a massive slump estimated to be 10,000 to 20,000 years old. This wasn't just a hillside, it was a colossal mass of unstable rock, roughly 2 kilometers wide and 1.8 kilometers long. This sleeping giant was characterized by a distinct, prehistoric scar, indicating past movement. Crucially, the rock strata in this region, composed of limestone and marl, were steeply inclined towards the valley, creating natural slip plains. This fundamental instability was a critical, pre-existing condition. Number 17 highlights a foundational oversight, the initial geological surveys. While the ancient landslide on Mount Toc was identified, its true scale and depth were severely underestimated. Early investigations relied heavily on surface mapping and a limited number of boreholes. These methods failed to penetrate deep enough to fully comprehend the complex subsurface structure, particularly the presence of clay-rich interbeds and heavily fractured rock mass. The engineers, eager to proceed with construction, might have interpreted the data in a way that downplayed the risks. This lack of thorough, in-depth geoscientific investigation set the stage for later misjudgments, failing to grasp the sheer volume of potentially unstable material. At number 16, we uncover a critical detail, the bathtub shape of the ancient landslide. This isn't just a pile of loose rock, it was a coherent mass, moving as a single block along a defined slip plane. This plane wasn't flat, it was spoon-shaped, or concave, like the bottom of a bathtub, dipping steeply into the valley. This geometry meant that as the reservoir filled, water could accumulate in this bathtub, increasing hydrostatic pressure and lubricating the slip plane. It effectively created a massive natural keyway for the mountain to slide along. Understanding this specific geometry was crucial, yet its full implications were overlooked in the early stages. Number 15 brings us to the first major intervention, the initial filling of the reservoir in 1960. As the water level began to rise, it fundamentally altered the hydrogeological conditions of Mount Toc. The immense weight of the water, combined with its ability to permeate the porous limestone, started to saturate the mountain's flanks. This wasn't just surface water, it was seeping deep into the rock mass, filling fissures and the ancient slip plane. This initial filling, though seemingly innocuous, was the beginning of a process that would fatally weaken the mountain, slowly but inexorably pushing it towards instability. The mountain was effectively being waterlogged from within. At number 14, we examine the insidious role of hydrostatic pressure. As the reservoir filled, water seeped deeper into the fractured rock mass of Mount Toc and accumulated along the bathtub slip plane. This water didn't just add weight, it created immense pore water pressure within the rock. This pressure acts as a wedge, pushing the rock particles apart and reducing the effective stress holding the mountain together. Essentially, it lubricated the ancient landslide surface, drastically reducing the friction that prevented it from moving. The engineers understood hydrostatic pressure, but the scale of its impact on this particular, ancient landslide was tragically miscalculated. Number 13 brings us to the mountain's first clear warnings: microtremors and audible creaking. As early as 1960, shortly after the initial filling, residents in the valley reported small tremors, sounds of cracking, and slight ground movements. These weren't random occurrences, they were the mountain literally talking, signaling internal stresses and initial, subtle movements within the ancient landslide mass. These whispers were dismissively attributed to minor settling or the mountain getting used to the new reservoir. The critical failure here was to interpret these phenomena as benign, rather than as escalating indicators of a deeply troubled slope, already on the brink. At number 12, we confront a chilling precursor: the minor landslide of November 4, 1959. This event, occurring just before the dam was finished, saw a section of Mount Toc slope, about 700,000 cubic meters of rock, slide into the Piave River Valley, which was to be the site of the reservoir. This was a clear, unmistakable warning. It demonstrated the instability of the mountain and its propensity for movement, even without the full reservoir present. While this event led to some increased geological monitoring, it didn't fundamentally alter the project's trajectory or the belief that the larger landslide could be managed. It was a dress rehearsal, tragically unheeded. Number 11 squarely points to the tragic failure to heed escalating warnings. Despite the microtremors, the 1959 landslide, and persistent concerns from independent geologists like Leopold Muller, the authorities and project engineers continued to push forward. Reports detailing the mountain's instability were downplayed or outright ignored. Muller's groundbreaking work on rock mechanics and the progressive failure theory suggested that the mountain's movement was accelerating and irreversible, a concept not fully grasped or accepted by the project developers. The prioritization of project completion and the immense investment overshadowed the mounting scientific evidence, a fatal flaw in decision-making. At number 10, we uncover the powerful, often invisible, hand of economic and political pressures. The Vajont Dam was a symbol of post-war Italian resurgence and technological prowess, a massive public investment promising abundant hydroelectric power for a rapidly industrializing nation. With millions of lire already sunk into the project, and political careers tied to its success, there was immense pressure to complete the dam and bring it online. This created an environment where caution was often overridden by expediency, and dissenting opinions were unwelcome. The utility of the infrastructure became paramount, overshadowing the critical geoscientific realities staring them in the face. Number 9 highlights a subtle yet potent factor: engineering hubris. The engineers behind the Vajont Dam were among the best in the world, confident in their ability to design and build structures that could overcome nature's challenges. The dam itself was a testament to this, an elegant double-arch structure capable of withstanding immense water pressure. This confidence, however, extended to their ability to manage the unstable mountain. There was a belief that through clever reservoir manipulation, they could control the landslide's movement, or at least predict it well enough to mitigate risks. This overconfidence blinded them to the raw power of geological forces, leading to dangerous assumptions. At number 8, we turn to the disastrous reservoir management practices. Faced with increasing movement, engineers attempted a series of controlled filling and emptying cycles. The theory was that by rapidly drawing down the water, they could slow or stabilize the landslide. However, these rapid fluctuations had the opposite effect. Lowering the water level too quickly reduced the external buttressing pressure on the landslide toe, while the internal pore water pressure within the saturated mountain remained high. This effectively increased the shear stress on the slip plane, acting like a trigger. These desperate experiments only exacerbated the mountain's instability, pushing it closer to catastrophic failure. Number 7 pinpoints a specific threshold, the critical water level. Studies later revealed that the landslide's movement significantly accelerated once the reservoir reached around 700 meters above sea level. This level provided the maximum hydrostatic pressure to fully saturate the deep slip plains, while also reaching a point where the buoyant effect could most effectively reduce the rock's effective weight. Despite observing this direct correlation between high water levels and increased movement, engineers were repeatedly compelled to raise the water for power generation or, ironically, to study the landslide's behavior, crossing this dangerous threshold again and again. At number 6, we witness the terrifying acceleration of the creep. In the months leading up to the disaster, the landslide's movement dramatically sped up. From centimeters per day, it jumped to tens of centimeters, then to over 20 centimeters per day in the final week. By October 9, it was moving at a rate of 20 to 30 centimeters per hour. This wasn't a sudden event, it was a progressively accelerating failure, clearly observable and documented by monitoring instruments. This rapid, uncontrolled acceleration was the mountain's final, desperate scream, yet there was no decisive, immediate action to evacuate the valley below, showcasing an appalling lack of urgency. Number 5 reveals a final, critical error, the last-ditch attempt to lower the reservoir level. In the days immediately preceding the disaster, with the mountain visibly collapsing, engineers initiated a rapid drawdown. They believed this would reduce hydrostatic pressure and stabilize the slope. Tragically, it had the opposite, catastrophic effect. The quick removal of water from the reservoir reduced the external support at the toe of the landslide, while the internal pore water pressure, which dissipates much slower, remained high. This created an even greater imbalance, essentially removing the foot holding the mountain back, directly triggering the final, massive collapse. It was a desperate, fatal miscalculation. At number 4, we face the sheer, mind-boggling scale of the landslide itself. On October 9, 1963, roughly 270 million cubic meters of rock, soil, and debris, an area equivalent to about 2.5 square kilometers, ripped away from Mount Toc. This immense mass plunged into the reservoir at speeds estimated between 25 to 30 meters per second. To put that into perspective, imagine a mountain nearly 3 times the size of the Great Pyramid of Giza, collapsing in a single, terrifying instant. The sheer volume and velocity of this event were unprecedented, generating an impact force that no engineered structure, however mighty, could ever hope to contain. Number 3 zeroes in on the immediate, terrifying consequence, the instantaneous generation of a colossal tsunami. The 270 million cubic meters of rock displaced a corresponding volume of water within the narrow reservoir in less than a minute. This wasn't a gradual swell, it was an explosive, almost instantaneous displacement. The water had nowhere to go but up and over. Using cross-section animations, we can see how the landslide acted like a giant piston, shoving the water upwards with incredible force, creating a wave that surged hundreds of meters high within the confines of the valley. This sudden, violent hydrodynamic event was the direct agent of destruction. Coming in at number 2, we have the dam's ultimate test, the overtopping wave. Despite its immense structural integrity, the Vajont Dam was never designed to withstand a wave of this magnitude. The tsunami, after being generated by the landslide, crashed against the opposite side of the valley, reflected, and then surged back towards the dam. A wave estimated to be over 250 meters high, more than twice the dam's own height, crested over its top. While the dam itself remarkably held, the water that poured over it was the true destroyer. It pulverized the village of Longeron and others below in an instant, a horrifying demonstration that even the strongest man-made barrier can be overwhelmed by nature's fury. And the number 1 factor, the most tragic of all, the catastrophic failure to evacuate. Despite mounting evidence, escalating warnings, and the final, undeniable acceleration of the landslide, no official evacuation order was given to the villages downstream. There was a communication breakdown, an underestimation of the imminent threat, and perhaps a reluctance to cause panic or admit failure. The decision to prioritize maintaining operations, even for a short time, over the absolute safety of human lives, sealed the fate of nearly 2,000 people. This ultimate human failing, the choice not to act decisively when disaster was knocking, turned a geological event into an unparalleled human tragedy. The Vajont Dam disaster stands as a stark, permanent reminder.